Before going to start, let I welcome Dr. Satish Kumar Singh for this session. And sir is my colleague and friend at IIIT Allahabad, and his area of interests are basically computer vision and deep learning. So before further going to start the lecture, I will request Upen, are you here?
Yes, sir.
Hello.
Yes, start the proceeding, please.
Hello. Hello.
Welcome everyone. The second session of the day will be taken by Dr. Satish Kumar Singh. Dr. Singh is currently serving as an associate professor in the Department of Information Technology at IIIT Allahabad. He is having more than 15 years of academic and research experience in various capacities. Presently, he is heading the Computer Vision and Biometrics group and is also in charge of Computer Vision and Biometric Lab. His areas of research include image processing, computer vision, biometrics, deep learning, and pattern recognition. In this talk, he will be covering the essentials of deep learning and its applications. So, over to you, sir.
Hello.
Yes, you are audible, sir.
Okay. So I like to thank the organizers for giving me a chance to speak in this course by Atal Academy. So I'm not going to take much time, and let me share my screen. So is it visible?
Yes, yes. It is visible now.
Okay. So the title of my talk is Pre-Deep Learning Essentials. So basically, we might have seen many courses by various standard organizations, various universities and other places. So today, deep learning is a buzzword, and almost everybody is willing to do some sort of research or willing to gain the knowledge in the area of deep learning. Okay. But what is our observation? What is my observation? That if we talk about young faculty members or young researchers, then they employ a lot of hit and trial kind of thing. Means the purpose is to solve any problem, maybe classification problem, or maybe any recognition problem. But what is the approach? Approach is simple. Means some echo is coming. Hello.
Yes, sir, you're audible.
Yes. So I request all the participants to please switch off. Keep their mics on mute so that no echo will be generated. So in the meantime, if anything is required to be discussed, then please raise your hand, or you can write on chat box, and then we can discuss. So the general approach for designing or applying any deep learning models is simply we take any pre-trained models, or we simply add some layers, some functions, and we employ it for solving some purposes. And we do many trials, and the trial for which the results are best, we adopt all those parameters. Means we decide the number of layers, the kernel size, okay, the optimizer, the nonlinearity function, etc., etc. Everything is defined basically post facto. Means after doing a lot of experiments, we used to decide all those things. So the purpose of the talk, today's talk means whether we consider the deep learning as a black box or deep learning concepts are developed on top of the concepts which were developed long back. in 1980s or even before that. Okay, so this is the first purpose. Second purpose, how we should choose various things, various building blocks of the deep learning architecture. Means what should be the scientific basis for selecting those blocks or various of those blocks. Whether this should be selected on the basis of hit and trial or random, or there must be some scientific basis for this. So with these pretexts, let me start the discussion. As the topic is pre-deep learning essentials, obviously we are going to discuss about many small things which were developed long back, and somehow we overlooked those concepts and we suddenly jumped into the business of this deep learning architectures, maybe CNN, maybe RNNs, maybe LSTM, maybe GAN, or whatever you think. Okay, this is sudden jumping, and somehow there is a gap. The gap was created just because the neural network was completely died out. It was finished because of many reasons. Okay, so I will try to correlate. Means deep learning is not a new concept. It is based on all those previous concepts. So let me start the discussion with this simple figure. Here, what we can see, the linear discriminant function and decision surfaces. We will discuss about these things. So here, Gx is W transpose X, W naught. Okay, so Gx is a function that depends on the value of X. Okay, so if there is a proper value of X, then the function will have certain value. Obviously, if we go through this figure, these are various small, weights, W naught, W1 to WD. Okay, and X1 to XD is D-dimensional data or input simply. And here, the function, which kind of functions are being used, these are the identity function, you can say. Whatever will be applied here will pass through this unit. Means there is no change between the input to output if we consider only this unit. So all those functions are the identity functions, you can say. Whatever input will be applied, output will be obtained the same. So a discriminant function, that is linear combination of the components of X, basically. So Gx is W transpose X plus W naught. We call this function as a linear, but this is not exactly the linear function. Okay, this is a linear combination, but why this is not a linear function? Because there is a basic thing that in very crude words, if any complex process can be represented with the help of only matrix multiplication, then only we will call this process as a linear process, or the function, this function will be treated as the linear function. But there is one addition here. Okay, so we are having the matrix multiplication along with some addition. So this is not a truly linear process, but somehow we can make this process as a linear process. That is fine. Okay, it means discriminant function that is a linear combination of components of X can be written in this form. The class of solutions that can be obtained from hyperplane discriminants are surprisingly good on a range of real valued problems. Means variety of problems can be solved, okay, even by this representation. Okay, but simply not general enough in demanding applications. Okay, for simpler problems, this equation may solve the purpose. Means linear discriminant functions may solve the purpose. But if we consider the complex problems, then obviously this kind of representation or this kind of solution may not be adequate, basically. Okay. So let me connect. Suppose you're having some data. Data may be a two-dimensional data. Here, this image is a two-dimensional data. So how many pixels? So 32 by 32 by 3. So total number of input data points are 3072. So this is quite big number. So 3072 input data points are there. And that is passed through a function which depends upon the value of x. X is the input and w is some unknown. Unknown means collection of some unknown values, you can say, at this point of time. And there are 10 numbers giving classes. Suppose means there are 10 classes. So this is simple classification problem. And using this parametric approach means this f will depend upon some parameter, maybe from any distribution. W may have any kind of distribution. X may also have some sort of distribution. So f depends upon x and w, means functional representation. And ultimately 10 classes or 10 numbers must be generated at output side. Means this f will have those 10 values, or you can say 10 classes. So fwx is wx. So how many values of f? Total 10. So f is a 10:1 matrix. Okay. And x, this w is 10:3072 matrix, basically. This w means how many values of this w? So 10 rows corresponding to 10 classes. 10 rows corresponding to 10 classes. And 3072 columns corresponding to number of data points. If we increase the number of data points, it means if we increase the size of this image, then this number will increase. Okay. If the number of classes are increased, rather than taking 10 classes, 100 classes, then this 10 will be changed to 100. So depending upon the number of classes and number of input data points, the size of this W matrix will be defined. It means if you want to use bigger images and more number of classes, so obviously the size of W matrix will be very, very high. Very, very high. Got it? But if we keep the size of image very small, then what happens? There will be less number of values in this W. Okay. And how many values for this X? So here 3072 by 1. So this is the vector, input vector. Okay. And we are using some bias terms. So obviously the size means the dimension of this B or the bias vector is simply 10:1, means the number of classes. So the same thing, linear discriminant function can be represented using this notation. So there is a straight correlation between these two. Means linear classifier and linear discriminant functions can be used in analogous way, or you can say can be used exchangeably. So let us explore this very simple problem. I said if there are 10 classes, then this W matrix will have 10 rows. Okay. And how many columns will be there in this W matrix? Depending upon the number of data points. So here, suppose there are only 3 classes, cat, dog, and sheep. So that's why this W matrix will have only 3 rows, and there are only 4 pixels per image of those 3 classes. So that's why there are 4 columns. Okay. So W matrix, initially, suppose this W matrix is having any random distribution, or those numbers are selected randomly. Okay. And input is passed or arranged in this way, including some biased values. Then after doing this mathematical process, the cat score means first row is defined for the cat, second row is defined for the dog, and the third row is defined for the sheep. So what is our objective? Our objective, if we are passing the cat image, then obviously the first input here must be maximum. If we are passing the dog score, then only the second element should be maximum. If sheep, then this must be maximum. But initially we selected random W. We passed some cat by choosing proper some values of these bias, and then we could get these scores. Certainly, this is not a cat as per the scores obtained. Then what should be done? What is the intuition and what should be done? Okay, then intuition is very simple. We should maximize value. We should maximize this value. At the same time, we should minimize these values for this data. Then by intuition, simply we can do this thing. You apply some sort of experience and choose those weights. You simply tweak those weights because these are very less number of weights. You tweak these weights, okay, to maximize this value. At the same time, you tweak these weights to minimize those values. Okay, so you present first cat, okay, you modify these weights to maximize the cat score. Then second cat image. Again, there may be some error. You optimize this thing. You slightly tweak those values. Okay. So after, suppose you're having 50 samples. So after 50 samples, you have fixed the weights of first row. Suppose you have fixed the weights of first row along with the weights of other rows, so that we have minimized those scores. And if we start presenting the dogs, again, we have to tweak those values just to optimize the score for the dog, and similarly for the sheep. So here it looks very simple process. It looks very simple process. It means we have to get the most suitable value of W, okay, so that for cats, cat score must be optimized, for maximized, for dog score, and for sheep score must be maximized. Other scores must be minimized. So after some time, these weights will be fixed. So basically, in machine learning, we adopt the same thing. We present the labeled data, and then this will fix itself. Maybe by applying some heuristic, or maybe by applying some experience, or maybe by applying some mathematical process. Okay. So this is possible. Means there must be a point where we can compare those values. So that point for the comparison will be simply known as the ground truth. And we have to compare with the ground truth. And depending upon the error value, this information will pass here, and this information will be used just to change the values of those first row and other things. The same process will be applied for all sort of training data. So this is simple process of learning. And whenever unknown sample comes, okay, it will be presented here, and it will be operated over this trained matrix, okay, and then a corresponding score will be generated, and depending upon the corresponding score, we will say, okay, whether this is cat, dog, or sheep. Means unknown sample is cat, dog, or sheep. So this is simple learning process. Okay, but what is the problem? If the size of this W is very, very large, then optimizing the value of W is very critical, very tough process, suppose. Okay, if we consider 1024 by 1024 image, then you can imagine how many data points will be there. And if there are 1,000 classes, so 1,000 rows, and even, I mean, you can consider, okay, lakhs of the columns. Okay, so optimizing such a big matrix is very difficult process. And this is typically, I mean, this is simply the linear classification problem. So here, linear classifier will be interpreted. For example, there were 10 classes. So those discriminant functions will be obtained. Okay. And for plane, car, bird, and all those things, for all those things, there will be some representative values. Okay. And any unknown sample which is nearest to any out of these 10 representative samples, then that will be predicted with that. Okay, so this is very simple process. So here I said, okay, this is not a complete linear process. So there is a trick. Simply you include this bias term with this, and you add one more column to this data matrix. So simply you have added this and you included this one more column. So now there are 3 by 5 W matrix, and X is increased by one more dimension. Okay, so this way, and now this is completely represented by only matrix multiplication, and this is truly linear process. This function depends upon X, W, and B. If B is merged into W, then you can say, okay, X and W, that is fine. Okay, so this is complete linear process. So basically what happens in case of three class problem, 3 decision boundaries will be formed. Means all the samples above this boundary will be predicted as car, and below this non-car. Here, deer, non-deer. Similarly, airplane, non-airplane. So basically these kind of decision boundaries will be formed. And if the number of classes are very high and samples are also very high, then this is very difficult to form, or I mean, this is very difficult to separate the data by using this linear technique. Means some of the data will be submerged. Means one class will be merged with the second class, and then it is very difficult to differentiate between or among those classes. Okay. So these are very small problems. I mean, very hard cases. Although there are only 2 classes, but linear classifiers cannot form the decision boundaries to separate these 2 classes. This type of distribution, or maybe this type of distribution, or this type of distribution. There are possible many such distribution having only 2 classes. And it is very difficult, means almost it is impossible to separate those classes by using the linear discriminant functions or linear classifiers. So the above problem can be solved with the help of non-linear classifier. If this kind of distribution is there, okay, if this kind of distribution is there, then how these kind of problems can be solved? These kind of problems can be solved by using non-linear classifiers, by selecting the appropriate non-linear functions. Appropriate non-linear functions. Okay, so a brute approach. So which non-linear function must be used? So a brute approach might be to select a complete basis set, such as all polynomials. All polynomials means whatever polynomials are available, you simply use all those polynomials, you do the hit and trial and try to optimize it. So this may be one approach. So such a classifier would require too many parameters, to be determined from a limited number of training. No automatic method for determining the non-linearities when no information is provided to the classifier. Okay, which type of means which non-linear function must be used means selection is quite difficult. So what has been thought? Multi-layer neural networks may learn the form of non-linearity from the training data. Rather than applying the brute approach or doing the hit and trial, multi-layer neural networks have been used where which kind of nonlinearity is present with the data, if it is not known prior, will be explored by the network itself. It means multi-layer neural networks can give a possible solution for such difficult problems. So let us discuss neural networks without the brain stuff. So linear score function. So for linear classifier means F is WX. This is representation for linear classifier. How this linear classifier will be converted into non-linear classifier. So F is W2. Here we have used a max function. For two-layer neural network, here we have used a max function. So max function is basically a non-linear function. Means it selects either 0 or W1x, whichever is maximum. Means out of these two values, maximum value will be selected by this function. So basically this is a non-linear function. So we have included this non-linearity into the linear classifier or linear discriminant function somehow. Okay. Similarly, for three-layer neural network, W3 max, okay, 0, W2 max, 0, W1 max. So there is chain kind of representation, means we are using max function as the nonlinear function. But here, it is not necessary to take both the function as a max function. Means it may be different, it may be different. Both the functions may be different. Different nonlinear functions may be used. But here, just for simplicity, this kind of representation has been done. So linear function, it means linear score function is represented this way, and neural networks are represented this way by using the nonlinear max function. So this is simple neural network representation. Number of input 3072. Hidden units, suppose there are 100 hidden units used and S output, so there are 10 classes. So X to H, this is W1 matrix, H to S, W2 matrix. Okay, so this is simple representation. Means how we are, actually we are converting this linear function into non-linear function, or we are just correlating the linear function with the neural networks. So if we remove this linear function, is it possible to correlate? Means how neural network can be converted into linear classifier. Where neural network is a non-linear classifier, it means what is the correlation between linear and non-linear classification or classifier. So here, this is simple active. This function is simply known as the activation function, which is non-linear in nature. If we remove this function, okay, and if we use the identity function, okay, so this representation will be converted into this form. So again, I have already said that if any complex process is represented in the form of matrix multiplication only, then this is linear classifier. So we can say W3 is W2, W1. So F is W3 into X. So this can be represented in this form. So neural network is converted into a linear classifier. So we end up with a linear classifier again. It means there is a relation between linear classifier and non-linear classifier. If you want to make a linear classifier into non-linear classifier, you introduce some non-linear function in between. That's it. And the classifier will be converted into nonlinear, and vice versa. It is possible. So, limitations of the linear machines. So basically, if the distributions are like these, so there are only two classes. Here also there are two classes, but it is very difficult to form the decision boundaries or linear decision boundaries. So it is almost impossible to classify these kind of data distributions. So this is important. Number of linearly separable dichotomies. Okay. So at y-axis, what is there? Probability of linearly separable. Means linear separability probability at y-axis. And at x-axis, the number of samples are there. Okay. Number of samples. So what we can perceive? If the number of samples are increasing, then linear separability probability decreases very quickly. And where it is a compromising when the number of samples are equals to the number of, the dimension of the vector. Number of samples are equals to the dimension of, it is 0.5, so this may be a compromising point. Up to this it is fine. But if the samples, number of samples are very large compared to the dimension. What is the dimension? Dimension of the representation. Means the dimension of the feature vector. Then what happens? The linear separability probability decreases very quickly. So the probability that p samples of dimension n are linearly separable goes to 0 quickly as p grows larger than n, as per this Cover's theorem, which was introduced in 1966. So now can you correlate between this elaboration and curse of dimensionality kind of problem? Means there is some sort of relation and projection from one. If we talk about the kernel machines, can you correlate with this theorem application? Means there is a direct relation between the Cover's theorem and the kernel machines. You can say, if we talk about the SVM, and why we use a mapping from lower dimensional space to higher dimensional space. So let us be curious. Problem. There are 2 to the power p possible dichotomies of p points. Only about n are linearly separable because the probability is about 0.5. So if p is larger than n, the probability that the random dichotomy linearly separable is very, very small. If Cover's theorem is true, okay, and if we are having large number of samples, then what is your suggestion? So there is obvious suggestion. Either you decrease the number of samples or you increase the dimension of the feature vector. There are only two solutions. Either decrease the number of samples or increase the dimension of the feature vector. It means this is not random. This is not random. There is a proper basis for deciding this thing. Then what we used to do actually. So these are hard cases. Making n larger. So we apply some sort of pre-processing. What is that? Means we want, because we have given all the samples must be decided. We cannot decrease the number of samples. So what is the other solution? Simply increase the n, make n larger. How this n can be made larger? You do some sort of projection from lower dimensional space to higher dimensional space. Projection from lower dimensional space to higher dimensional space. Now you remember from SVM to kernel SVM. Okay. Now you can correlate this thing. Here, What is happening? The input vector was having only dimension 3. You applied some function phi x, and now it has been converted into 1, 2, 3, 4, 5, 6, and 7. From 3-dimensional space to 7-dimensional space, and then we applied the process, and then in that space it can work similar to the linear, but in original space it may be non-linear, means originally the data may be non-linearly separable, but in projected domain or projected space it may be linearly separable. Okay, and there it will be separated, and then we can draw the conclusion. So what is required? As per the Cover's theorem, if we are having large number of samples, we have to increase the dimension of the feature vector by projecting from lower dimensional space to higher dimensional space. And that is exactly done even in case of linear and non-linear SVMs. That is done exactly in case of the all non-linear classifiers, maybe the neural networks as well, because we are projecting. If you consider the input matrix, dimension of input matrix or input vector is simply 10, and the number of hidden units are 100, then we are projecting from 10 to 100, and then we are trying to do the classification in that 100th dimensional space, basically. So we are just following the Cover's theorem. We are not doing anything new. Okay. So the answer, we make n larger by augmenting the input variables with new features. We map or project X from its original n-dimensional space into a higher dimensional space where things are more likely to be linearly separable using a vector function. It means randomly we are not doing, heuristically we are not doing. There is a proper ground for projecting from lower dimensional space to higher dimensional space, and this projection can be done in many ways. It can be done by applying some nonlinear transformation function. It can be applied, it can be done with the, in case of nonlinear SVMs, it can be done in case of the neural networks. So basically neural network does the lower dimensional space to higher dimensional space transformation. So this is typical XOR problem. We know very well this is a very difficult problem, how to solve with the help of neural networks. So here we can see this is very simple neural network architecture. These are the input. So these are the identity function. There is some nonlinear function at hidden units. Bias is represented in this way. So there is no issue. So basically, due to this, okay, output of this unit will be simply this function. This is complex function somehow. This is second complex function. These functions are added in using appropriate weights, and final distribution can be obtained in this way. Okay, final distribution can be obtained in this way. Got it? Means we can form the decision boundary. This is a complex decision boundary, but it can be formed with the help of these hidden units. Still, we can consider this as a simple problem. Okay, so a 3-layer neural network having input, output, and hidden layer. Okay, interconnected by modifiable weights represented by links between layers. So this is simple representation. XOR problem can be solved with the help of this kind of arrangement. But what are the flexibilities? You have infinite number of choices for these weights, basically. So final solution may one set, but for the second case, different set. Let's talk about multi-layer network application. What is that? Every decision be implemented by a 3-layer network described by equation 1. It is missing here because I have deleted few slides. So answer, yes. Yes, it is possible. It means any continuous function from input to output can be implemented in a 3-layer net given sufficient number of hidden units. sufficient number of hidden units, NH, proper nonlinearities and weights. What does it mean? In a different way, you can say only 3-layer networks are sufficient to implement any complex decision boundary. It means any complex nonlinear function can be generated with the help of only 3-layer neural networks, provided you should have infinite number of hidden units. It means we have to project appropriately from lower dimensional space to infinitely large higher dimensional space. Got it? If we can do this, it is quite possible. It is quite possible. It means these multi-layer neural networks are quite expressive, provided large number or sufficient number of hidden units, nonlinearities, and weights are selected. It means everything is possible with the help of only 3-layer neural network. Where is the cost? Cost is simple because you consider the Fourier transform. What we do in case of Fourier transform? Any function is disintegrated into infinite number of sines and cosines. Means infinite number, with the help of infinite number of sines and cosines added appropriately, means suitable sign and weights, any complex function can be generated. Any complex function can be generated. Similarly, here also, you can use large number of hidden units, and each hidden unit defines a discriminant function. It means you select infinite number of discriminant function, and that can be done. Means similar to Fourier transform or Fourier analysis or Fourier synthesis. In fact, the same thing is being done here. It means there is no difference. So consider this case. Here the final decision boundary is quite complex. You can consider this a two-dimensional bell-shaped structure. So this is quite complex decision boundary. How it has been generated? Here, rather than using 2 hidden units, as in case of the XOR, we have used 4 hidden units, and corresponding functions are being generated. You have added those functions appropriately, and final function can be generated. It means with the help of those 4 functions, this final function, output function, can be generated. This is a simple 3-layer net. So each hidden and output unit has sigmoidal transfer function. It may have any other transfer function as well. The hidden unit outputs are paired in opposition, thereby producing a bump at the output. I mean, appropriately you can add up those functions for generating any complex function with the help of only 3-layer net. So what is takeaway? Given a sufficiently large number of hidden units, any continuous function from input to output can be approximated arbitrarily well by such a network. It is possible. So if the distribution, data distribution is like this, there is a reason 1, there is a reason 2. Okay, it is very simple. We can use simple perceptron. So 2-layer network classifier can only implement a decision, linear decision boundary. 2 layers are sufficient, and we can do this kind of segregation. But if the decision boundaries are like this, okay, these are quite, although there are only 2 classes, but the distribution is like this, then we have to use 3-layer net with sufficient number of hidden units. It means how to decide the number of hidden units. So if you observe the data distribution and decision boundaries are quite complex, then you keep on increasing the number of hidden units and keep on optimizing. Okay, and then you can generate the complex decision boundaries. So for these kind of distributions, 3, 4 and higher layer networks can implement arbitrary decision boundaries. Means 3 layers are sufficient with sufficient number of hidden units, or at the same time, if there is a data variability. Got it? It means there are two classes of data, and interclass distributions are, interclass distribution is quite big. Big means quite skewed kind of things, you can say. Then you have to use, distribution is like this, but interclass distribution means interclass as well as intraclass, both. Means similar kind of object, means the same class. There is a huge difference in the same class as well as between the class. Okay, then you have to use large number of hidden units. At the same time, you have to add more and more layers. Why more layers are being introduced? Why to increase the number of layers? Depending upon the data variability for the same class. So provided adequate number of hidden units. So this is, and then the next development was the back propagation algorithm. We know very well. So basically, if here up to this point, for any complex problem, we have to select large number of hidden units, almost infinite number of hidden units. So if there are infinite number of hidden units, then the connections are also infinite, and the size of this W matrix is almost infinite or almost impossible to optimize. That's why neural network died off at this point. But somehow, means it was very difficult to optimize. But due to the development of the back propagation algorithm, okay, so for what it is used, our goal now is to set the interconnection weights, how to tweak the value of W matrix, okay, based on the training patterns and desired output. Means we are having label data or ground truth. On that basis, we have to set the value of W. So in a 3-layer network, it is straightforward matter to understand how the output and thus the error depends on the hidden to output layer weights. The power of back propagation is that it enables us to compute an effective error for each hidden unit, and thus derive a learning rule for input to hidden weights. This is known as the credit assignment problem in analogous way. It means it compares with the ground truth, find out the error is increasing or decreasing, so it will find the rate and it will be back propagated. Means to tweak the weight of W. That's it. So there are basically two modes of operation. I'm just skipping. So there may be feed forward or maybe learning. So this is general representation. D, NC, H fully connected 3-layer network. So input, hidden unit and output. That's it. So network learning. How network learning happens. So I have already discussed. It means it will find out the error between the generated output as well as the ground truth. And then will find out the error rate, and it will pass to the input side just to tweak the value of W. And it will keep on iterating until it is optimized for all classes, all data. So the weights are initialized with pseudo-random values and are changed in direction that will reduce basically weight updates. So W means this delta W must be reduced. Means it should be fixed somewhere. It should be fixed somewhere. That somewhere may be anywhere, but it should be fixed. Means after certain iterations, this W should not change. And when W will not change, when delta W will be 0, ideally. So delta W is defined as minus eta del J by del W. What is J? J is the error. Basically error between the obtained result and the ground truth. So where eta is the learning rate, which indicates the relative size of the change in weights. So if eta is more, delta W will be more, whether positive or negative. Means whether we need to increase the weight or we need to decrease the weight, depending upon the value of eta. So error on hidden to output weights is defined as del J by del W Kj, where K is the output, J is the hidden, and I is the input. So this is, we can find out all those things. I'm just skipping. Okay, you can refer or I can explain, but it will take more time. So we will find the weight update or learning rule for the hidden to output. So delta WKJ will be found out. So eta delta K Yj, and this way eta Tk minus Zk F dash means this is the first derivative of net activation and then Yj. Similarly, input to hidden can be obtained and final learning rule can be defined. So this is the input to hidden. And this way we can update the weight between input to hidden and hidden to output depending upon the value of, means error. What is error? Output and ground truth, means the difference between the output and ground truth. That can be, means this way the weights can be updated. So by using the back propagation algorithm, this is possible to update or change the weights. Then if we are changing the weight, then after some time the weights must be fixed. Means you will consider the machine has learned properly. Now we should stop the process. Then where to stop the process and how to stop the process? The algorithm terminates when the change in the criteria function J, W is smaller than some preset value, maybe theta, well-defined or predefined value. There are other stopping criteria that lead to better performance than this one. So you can consider, okay, after 100 iteration, we will stop, whether it is minimized or not. So we can tolerate only up to 100 iteration. It's fine. Or you can tolerate up to 100 epochs or 2000 or 4000 epochs. It's fine. Means we will not see the minimum value. Okay. We are not going to zero it, but we will stop somewhere. So far we have considered the error on a single pattern earlier. Means this error will be calculated for all the training data and it will be accumulated and then it will be optimized. But we want to consider an error defined over the entirety of the patterns in the training set. So total error, training error is the sum over the errors of n individual patterns. So you sum up all those errors, okay, for n patterns and then optimize it. So the weight update may reduce the error on a single pattern. It means if you update the weight, why this is adopted basically? Why used to do this accumulation and then weight updation? We could update the weight step by step. You present the data, you update the weight. You present the next data, again update the weight. So this kind of iteration is possible. But there are certain issues. A weight update may reduce the error on single pattern, okay, being presented, but can increase the error on the full training set. It is possible. So, however, given a large number of such individual updates, the total error of equation 1 decreases. It means if you update every time, depending upon the data presentation, then there may be more oscillatory nature. Means sometimes you have to increase, sometimes you have to decrease, again increase, decrease. This kind of oscillations are possible. But if you do in average sense, then certainly it decreases. So that's why you accumulate the error and then optimize. So feed forward neural network variations. What are the possible variations of any network, neural network? So input units are connected directly to output units. This is possible, as well as to hidden units. These are the variations. There are more than 3 layers of units. Maybe more number of layers can be included in the neural network. There are different nonlinearities for different layers. So normally, just for simplicity, we use or we choose the same nonlinear function for the each layer. Say there are 3 hidden layers, okay, or maybe 2 hidden layers. So from input to hidden 1 to hidden 2 to output. So normally what happens, we can have the same nonlinear function, same kind of nonlinearity can be employed on each and every unit, or each and every unit may have different nonlinearity. Means it is not necessary that each unit of the same layer should have the same nonlinearity. It may have different nonlinearity. Means all different nonlinearities can be used. Okay. So each unit has a different learning rate as well. Means eta is not same for all the units. It may be different for different units. But what will be the problem? Problem will be simple. While applying the optimization, okay, we have to select variety of eta, variety of nonlinearities. So the process will be very, very complex in nature. So this way, basically, if we are having these kind of flexibility, learning algorithms can be generalized. It means we can develop those learning algorithms for variety of problem, or you can say in crude words, for all sort of problems. Then protocols. Here, we have seen that what is the need to accumulate the error. Okay, it means just to avoid the oscillatory nature during the weight optimization. Okay. So let us try to link. So there are many training protocols. So stochastic training. What does it mean by stochastic training? Sometimes we use those terms. Okay. So patterns are chosen randomly from the training set, and the network weights are updated for each pattern presented. So you're having 1,000 samples. Out of those 1,000 samples, you select randomly 10 or 100 samples and update the weight. That is fine. But this is a random. So this kind of training is stochastic training. Okay, means you present one by one those 100 samples only, which were randomly selected from the space. Second one is the batch training. All patterns are presented to the network before learning weight update takes place. It means all patterns are presented to the network before training or before learning. What does it mean? Means what is the meaning? Means you present all the data, accumulate the error, find out the total error, okay, and then update the weight. So this is the batch mode of training. So batch mode of training is sometimes useful just to avoid the oscillatory nature of weight update. But in case of online protocol, each pattern is presented once and only once, and there is no use of memory for storing the pattern. There is no use of memory for storing the pattern. But in earlier cases, you should have all the patterns prior to training. But in this case, if there is a scenario when you're not having the flexibility of having prior samples or prior patterns, then you should adopt this online training protocol rather than using the stochastic or batch training protocol. Okay, so these things are, so basically there are 3 training protocols, including some other peripheral things like learning with queries. The output of the network is used to select new training pattern. The output of network is used to select new training patterns. Okay, this kind of learning can be done. And here we should understand what is the meaning of epoch. The number of presentation of the full training set. You present the full training set once, it is one epoch. Okay, you accumulate all the weights, I mean all the error, and then update the weight. Then second time present all the sample, accumulate the weights for all the sample, and then again update. So how many times weight update will take place? Number of epochs. If there are 100 epochs, 100 times weight update will take place. Although in a single epoch, there may be 1,000 samples. But updates are only for 100 times, depending upon the total number of epochs being used. So these are some basic terms, basically, which were given in the basic theory of multi-layer neural networks and other things. But somehow, nowadays, these things are again being used. Learning curves. Before training starts, the error on the training set is high. Through the learning process, the error becomes smaller. The error becomes smaller. So you consider an example. There is a kid and you want to make the kid to learn the apple. Means identify the apple and maybe orange. So what need to be done? Initially you present the apple. The kid may not know apple. He may say, okay, something different. Or you present the apple. He may say, okay, this is orange. Or orange to apple. It is quite possible initially. But what happens? You keep on repeating the process. You show the apple. Kid may say, okay, this is orange. Then you correct it. No, this is apple. Means ground truth. And then optimize. Next time, the kid may say apple. Again, it may say orange. Then again optimize. So this way, after some time, kid will be very, very familiar. And it will say, okay, you present the apple. He will say, okay, apple. Or you present the orange. He will say the orange. So initially, the training error is quite high. But in due course of time, this training error will certainly decrease. Will certainly decrease. Okay? And every time there is a scope of guava and banana, but every time, 99% of the time, you are presenting and making the kid to learn only apple and orange, then what happens? What happens? Okay? Okay? The kid will overlearn. Kid will overlearn. Training error will keep on decreasing, and the system will be overlearned, or in technical terms, you can say overfitting may happen. Overlearning of the system. Some sort of overlearning. What does it mean? You present something different thing, kid will say, no, this is apple or orange. Apple or orange. If you present the guava which is slightly similar to apple, he will say, no, this is apple. It means less generalization capabilities. Generalization capabilities are lost, means analytical capabilities are lost. System is highly biased now. Means, do we need this kind of system? Do we need to decrease the training error up to zero? No. Otherwise, it will be a disastrous situation. We need not to decrease the training error up to zero. Otherwise, it will be highly biased system. Okay? And there will be problems. Generalization capabilities of the system will be ended. Means there will not be any generalization capability to that machine's learning system or learned machine. So somehow it is not advisable to minimize the training error. Okay? It is never advisable to minimize the training. Okay, it should be as minimum as possible, but it should not be the least. The error per pattern depends on the amount of training data and the expressive power, such as number of weights in the network. So this is well known. We have already discussed this thing. The average error on an independent set, a test set, is always higher than the training set. And it can decrease as well as increase. What does it mean? We have trained the model and slightly unknown samples are being presented. If your system is having excellent generalization capability, then obviously testing error should be as minimum as possible. But if the generalization capability is not good enough, okay, which will happen after some time. Although training error will keep on decreasing, but after certain time, due to bias, this generalization capability will start losing. And at that point, your testing error will keep on increasing. Why? Because unknown samples will be presented and your machine will not be enough intelligent to generalize. this newly presented data. Okay, so that's why testing error may decrease, and it may increase from the point from where the generalization capability of the machine is being lost. So a validation set is used in order to decide when to stop training. It means which point must be selected. So we do not want to overfit the network and decrease the power of classifier generalization. So we stop training at a minimum of error on the validation set. We train the network, and every time as we are training, you present some unknown data and find out the error. Okay, that will be the validation error. And again train, again find out the validation error. Again train, again find out the validation error. So simultaneously you can find out the training as well as the validation error, as well as the testing error. Got it? So you plot simply. Okay, and here training error is continuously decreasing. Here you can find out. But testing error is decreasing, and after some point it may increase. Why it is increasing? Because the generalization capability of the machine is being lost, is decreasing. So what should be done? We can use the validation data, so we can stop. Means after this point, okay, after this point, there is an indication that means validation error is minimum. So after this point, the test error may increase. Okay, so this is a compromising point. We are not selecting this training error. Otherwise, for this training error, the test error is very high. Okay, and the machine's generalization capability is completely lost. So this is not intelligent machine. So here we should select this point of deflection. It means we in this case, we should train between 4 to 5 epochs. We can choose 4 epochs or only 5 epochs. We should not go beyond that. If we go up to 11th epoch, although the training error is minimum, but the test error will not be minimum. Okay, if we are using only training and test to decide. Okay, now there is a question from this curve. Suppose if machine's generalization capability is being decreased, then what need to be done? What need to be done? We are presenting apple and oranges, and kid is overlearned now. It is highly biased. Then what need to be done? We need to be done every time you present slightly noisy apple and noisy orange. Means slightly different. Means not similar kind of apple or similar kind of orange. You every time you present slightly different or learn with some sort of noise. This simple, you can consider this noise as a regularization term, you can say. Means you have added some sort of noise. Every time you are adding some sort of noise, then every time machine will try to generalize. So this way the generalization capabilities of the machine will keep on increasing. Okay. So these things are there. So practical techniques for improving the backpropagation, most important consideration is selection of architecture and selection of parameter. So our goal here is to give a ethical basis for making such choices based on learning speed and optimal recognition performance. Learning speed and optimal recognition performance. How quickly it will learn, there is one thing. And what is the accuracy, you can say. That is another thing. Those things are being considered basically. So we can talk about the activation function. So there are some basic requirements. Backpropagation will work because we need to take the derivative and the sign of the derivative also. So that's why first derivative, second derivative, both need to be taken. This is the basic requirement. So backpropagation will work with virtually any transfer function, provided a few simple conditions are met, such as continuity of f and its derivative. F should be continuous and should be derivable, basically. in any particular classification problem, we may have a good reason for selecting a particular transfer function. Means that may depend or differ problem to problem. For instance, if we have prior information that the distribution arises from mixture of Gaussian, you understand this thing. Sometimes the distribution is Gaussian distribution or mixture of Gaussian distribution, then Gaussian transfer functions are appropriate. If it is Rayleigh kind of distribution, Rayleigh may be useful. I mean, randomly, some sort of guessing can be done, but this guessing is not the random guessing. This guessing is somehow informed guessing. So you can select those transfer function on the basis of some prior information about the distribution or data distribution. That's it. So F must be nonlinear, otherwise the 3-layer network provides no computational power over that of the 2-layer network. पहले हमने देख लिया. We have already discussed this thing. We have to introduce the nonlinearity. If it is not nonlinear, then there is no difference between the linear classifier and nonlinear classifier. Purpose will be wasted. Must saturate, have a maximum and minimum. Otherwise, the weights and activations will not be bounded. Weights and activations will not be bounded. What does it mean? And the training time will not be limited. If it is not bounded, you cannot guarantee for the optimization. It can settle anywhere. It can settle anywhere. No saturation point, nothing will be obtained. So that's why it should be saturable in nature. Must be continuous and smooth. So F and F dash means first derivative be defined throughout the range of their argument. Otherwise, back propagation will not be feasible. Must be monotonic. Derivative have the same sign throughout the range of the argument. Okay. Otherwise, additional and undesirable local extremum in the error surface may be introduced. Means there must be a proper basis for the selection of the activation function. Okay, there are some basic requirements. At the same time, one clue can be drawn from the data distribution as well. Linearity for a small value of net means which will enable the system to implement a linear model if adequate for low error. It means the system should automatically convert from non-linear to linear for low values of the error. Got it? Initially it is non-linear, it will keep on learning. When error is minimum, so this is as good as a linear classifier. It is completely trained. It has projected and now it is trained. So sigmoid may be a common choice. It is very old, okay, a function which was actually used earlier, but there are now many modern functions which are being used in case of deep learning. But every time there are certain basic requirements which should be fulfilled, otherwise learning cannot be completed. There is another thing, data standardization. What is data standardization and what is the need? The full data set should be scaled to have the same variance in each feature component. Or data mining, okay? The full data set should be scaled to have the same variance in each feature component. There is example in a fish classification problem, fish length in meter. So what is the range of gram? It may be 100 grams, 200 or 500 grams. In meters, it may be 0.1 meter or maybe if it is 100 centimeter. So it is 0.1, 0.01 kind of thing. It means one means in this feature vector where weight and length is being considered, which one is dominant? The weight is dominant because the numerical value of the weight is more compared to the numerical value of the length. So length will not have any role in classification. So error hardly depends upon the tiny length values. Similarly, if fish weight in kilograms and fish length in millimeter, then again Kilograms, it may be 0.1, 0.25, 0.01 kind of thing. And millimeters, maybe 100 millimeters, maybe 200 millimeters, etc., etc. So here, length will dominate. Okay. So what is suggested by intuition? Both the things may be between 0 and 1. If we do this kind of standardization, it is possible. It may be between 0 and 1. But what happens? How to find out the maximum of the weight and maximum of the length from the data? It is sometimes quite impossible to find out. So sometimes it is not possible to standardize by using the maximum value. So variety of data standardization techniques are available, but somehow it is essential. We should do some sort of data standardization. Otherwise, it will create some problem during the classification or any machine learning task. So naturally, we do not want our classifier to prefer one of these features over the others, since they differ solely in the arbitrary representation. So in order to avoid such difficulties, the input pattern should be shifted so that the average over the training set of each feature is 0. Moreover, the full data set should then be scaled to have the same variance in each feature component. So Z-score or min-max or max or any other normalization technique must be used for data standardization. And there are some appropriate choices for the target value. Target value should also be selected very appropriately. Otherwise, there may be problem because net value may differ. Okay. Since the output unit, in case of the sigmoid, saturates at plus minus 1.716, we might naively feel that the target value should be those values. Okay. However, that would present a difficulty. For any finite value of net k, what is net k? W into x. The output would be less than the saturation value, and thus error would be, there would be error. So what is suggested? Full training would never terminate, as weight would become extremely large as net k would be driven to plus minus infinity. Okay, so this is a problem. So for instance, in a 4-category problem, if the pattern is in category 3, the following target vector should be used: -1, -1, +1, -1. Rather than using the finite, these values, continuous values, we can have the discrete, somehow discrete values can be used for a particular pattern. Then, what is the role of training with noise? For a small training set, generate virtual or surrogate training pattern. Okay, use them as if they were normal training patterns sampled from the source distribution. It means if you are using the image of apple, you use slightly noisy apple so that it is slightly difficult to recognize as apple. Okay, then the kid will generalize. So for standardized data, added noise variance is less than 1. Category level is unchanged, although we have added the noise, but the category level
Satish
should be the
sir,
same. Yes, sir.
you may conclude in 4 or 5 minutes so that we may discuss more with the participants also.
Yeah, sure. So this helps most classification methods except for highly local classifiers such as the KNN. So basically, we should add some sort of noise just to do better generalization. Similarly, manufacturing data means manufactured data can also be used. So there is a difference between the noisy data and manufactured data. In case of the manufactured data, we do some slight variation in the data itself rather than adding the random noises, etc. So this is important thing, number of hidden units. So input vector will define the input unit. Classes will define the output unit, and hidden unit, it governs the network's expressive power. If we want more expressive power for complex decision boundaries, then obviously NH should be very high. Otherwise, we can keep NH small. But if we do this thing, For linearly separable patterns, NH may be small, but quite complex pattern, NH should be quite high. Means sufficient number of hidden units must be used with certain constraints. So here means how many hidden units must be used. Is there any rule or there is hit and trial method? So some experiments have been done, and on the basis of these experiments, a thumb rule has been formed regarding the number of hidden units. So a 2NH1 network with bias. So number of categories were only 2. So this is binary classifier, 2-dimensional pattern for each category. So there were 90 patterns for each category. So total number of samples would be 180. So total 180 samples need to be used or need to be classified, you can say, or machine may be trained by using those 180 samples. Okay. So here NH, so number of hidden unit is between 4 and 5. On which ground? When the train error is minimum, at the same time test error is also minimum. So when the test error is minimum, between this 17 and 21. So total number of weights. So total number of hidden units between 4 and 5. Got it? So total number of hidden units must be between 4 and 5. Where the total number of weights will be defined on the basis of these hidden units. So it is 17 to 21. So these many parameters will be needed to be optimized for getting the best performance in this case. Okay. So rule of thumb is networks with roughly n by 10 weights is most suitable. What is n? N is the total number of samples. So if you have large, here what networks with, how many weights? So n is 180. So 18, how many weights? 18 weights. 18 weights will come between 4 and 5. NH between 4 and 5. So say here. So 4 or 5 hidden units must be used in this case. If it is more than that, maybe 300, then it may be 30. So it may be between 7 and 8. So depending upon your number of samples used for training the network, your hidden units must be decided. Hidden units must be decided. And there is a clue. Means you can get a clue while training a network even in case of deep learning models. Means you can get a clue about the size of the kernel in case of the deep learning model. Although it depends upon some other receptive field and other things in case of vision and image processing applications, but certainly you can get some clue about the number of hidden units. Rather than doing the hit and trial for infinite number of settings, you can choose few settings and then you can optimize. So there are something about the weight initialization and other things. Assuming the fixed network topology and hidden units, okay. Weight initialization must ensure the fast and uniform learning. All weights reach their final equilibrium value at about the same time. So data standardization is positive and negative values equally. This will give on average, we want positive and negative weights as well. So for a given layer, weights are selected randomly for a single distribution to help ensure uniform learning. And other things, means there are so many things we can discuss. So somehow weight initialization is very important. Okay, and there are variety of methods proposed for initializing the weights in case of deep learning models. Then learning rate is also very important. What should be the optimal learning rate? Means what should be the value of eta? So here the eta optimal is defined as the second derivative of j with respect to w, inverse. Okay, that is the optimal rate because of this equation, and we can calculate this value. And there are certain things, if eta is less than the optimal value, then the learning will take place like this. So this is sure to learn. If it is optimal, then in one go it can get the minimum. But if it is between these two, okay, there may be bounce kind of operation. And if it is more than that, then we can never get, I mean, there is a possibility not to get this minimum value anytime. So certainly we should try to find out this value, okay? And then depending upon this value, we should select the value of eta, whether we need to keep lesser or equal, more. Normally it should be optimal. Okay, so I can stop the discussion. There are some other things regarding momentum, etc. So I can leave the discussion at this point, but remember, all those terms are very important and nowadays are being used in almost all deep architectures, and these things are having proper ground for using. These are not random. There is no black box, nothing. Everything is having some scientific value, scientific reasoning. So I'm just just stopping at this point.
So if the participants have any query and question for discussion, they may unmute and ask. Participants, if you have any question, please.
Since they are not asking, so let me discuss one more thing, learning with hints. So here, this is very interesting thing here. So what happens? We are training the network. For example, we are designing the network for face recognition. Okay, there is a purpose of face recognition. But here, while training, we have used two hints. What are those hints? Means we have categorized, we have labeled those faces as persons, P1 to P100, maybe 100 classes. At the same time, those 100 classes are divided into two super classes of male and female. So these H1 and H2 are male and female. These are actually hints. So while training, those hints will be used. Okay, means this network will adopt those weights. This network will adopt all those weights depending upon this information as well. But at the time of testing, we are not going to use or infer from this thing anything. Okay, you simply disconnect and you present the sample, and then you can get better accuracy. Means your network will be more capable because inherently it has learned about the male and female nature of the faces as well. Similarly, you can have the hint about what? Hint about the age group, etc. You can have the ethnicity, you can have the color, etc. So those hints can be used in case of typical facial recognition system as well. So this is very interesting. I mean, it was proposed long back, but nowadays people are proposing these kind of architectures for deep learning techniques, means deep learning applications. So sometimes people may understand, okay, these are new concepts, but these are actually not new concepts, but developed long back. So these are the things. So this is the last slide. So how many hidden layers must be used? Although 3 layers suffice to implement any arbitrary function, I have already discussed this thing. Additional layers can facilitate learning. What kind of learning? It is easier for a 4-layer net to learn translation than a 3-layer net. Means if there is a intra-class variability, then you increase the number of layers. So rather than using 3 layers, you add the 4. Rotation scale and other transformation than a 5-layer net. It means how many layers, how many hidden units we fixed. What should be the parameters we fixed? Means there is some sort of intuition. But how many hidden layers must be used? If you have used intra-class data variability, then you should use more and more hidden units. So there should be a proper ground of using the number of hidden units rather than using randomly. So now it is over. And if you have any query, we can discuss or we can end the session.
Oh, so anyone have any question, they may discuss. And I would like to thanks Dr. Satish for giving valuable insight and building blocks of ANN. And you can say the pre-requirement for the deep learning. Anyone who is interested to work further in the deep learning part, I'm hopeful that the discussion given by Dr. Singh will be helpful to you to understand the building blocks, including how many nodes, hidden layers, activation function, optimization function, because all these are important and very, very important building blocks in ANN and even in the deep learning. With this beautiful discussion on this in detail and micro level, I am hopeful that all the participants, those who are not knowing and those who are knowing too, will get the basics, and definitely they will build up their own models with these nitty-gritty. I am thankful to Dr. Satish for sparing valuable time and giving such a beautiful talk during this session. So with this, again, I would like to thank Dr. Satish for sparing valuable time. Thank you, sir. Thank you for giving time.
Thank you, sir, for giving a chance to interact or discuss about these basic aspects. Thank you very much. And thank you very much for organizing this wonderful event here at IIIT.
Thank you, sir. Thank you. Dear participants, now, as per the norm, already one email had been shared to you, so that very soon one Google Class questions or Google Sheet will be shared to you, where my request is all the participants must submit that sheet with solution. It's objective type, so you all must participate, because as per the Atal norm, you have to appear on this exams. So my request, you all must present. And time window we have kept long, so that even the sometime late, you must submit that assignment and that quiz. You have to appear. At 3:30, we will meet again for just brief 15 to 20 minutes discussion, some feedback and validatory session. And if someone of you are interested, they may open video and then you may discuss if any feedback and suggestion if you have. Apart from that, it is mandatory for all to get the certificate. Whatever the feedback online you are going to give us, that is one part. You have to give your feedback on the Atal portal also. That is mandatory. Here you may or may not, but I will request you may give someone, so that it will motivate also us to get the feedback from the audience, what they have their opinion on that. But that session will start sharp at 3:30. Okay. So we are going to share. Yes, anyone?
So sharing feedback link or we have to visit the Atal site?
No. Feedback link. One feedback link is in the Aviral portal. Once you go there, you have to submit. Okay.
Okay, sir. Okay.
One is that here we are organizing at 3:30, where you may give in that live one.
Okay, sir.
Okay. But that is one part. That is mandatory. Atal is mandatory.
Okay, sir. Okay.
Here it's up to your wish, but we will encourage if someone will come and share his view. So we will meet at 3:30. Okay.
Sir, thank you, sir.
So I'm going to share within 10-15 minutes the questions. You have enough time. Read it, but make sure you must submit from your single ID. If you have given the multiple ID, use only one ID and submit it. Thank you, and we will meet at 3:30. Sir. Thank you.